So in this video, we're going to take a look at a couple of examples of using integration by substitution involving some exponential and logarithmic functions. So our first example, we have the quantity 1 minus t multiplied by e to the 20t minus 10t squared. And we are integrating this with respect to t. That's what this dt on the end means. All right? If we were taking the derivative of this, then we would have to use the chain rule because of that exponent 20t minus 10t squared. So that is what we are going to let our u substitute in for. And because we need to change this integral into everything involving u's instead of t's, we also need to change our integration variable and that differential dt. So we are going to take the derivative of both sides here. The derivative of u, we're going to call it du. The derivative of that right-hand side is going to be 20 minus 20t, and that's going to be multiplied by our differential dt. And since we're substituting in, we don't have this exact quantity in our integral, so I'm going to go ahead and move that to the other side and solve this for dt. So we'll get 1 over 20 minus 20t times du equals dt. All right, so if we plug back in our integral, 1 minus t, we didn't do anything with that just yet, so I'm going to leave that. And then we've got e to the exponent here is what we called u, so that's going to be e to the u. And then dt is going to be replaced with 1 over 20 minus 20t du. Now we cannot integrate this until we have everything in terms of u's. We have to get rid of all of those t's. And the way we're going to do it is we are going to factor out the GCF and simplify this rational piece right here. So we've got 1 minus t multiplied by e to the u times, I'm going to factor out that GCF of 20 in the denominator there, and we'll get 1 minus t left in the denominator. And now we have a 1 minus t in the numerator and a 1 minus t in the denominator. We can divide top and bottom by that, and now everything that is left involves only u's. We've got 1 over 20, we've got an e to the u, and we've got a du. Now, integrating e to the u, those are, I like doing e to the u or e to the x dx. Those are the easiest ones because you don't have to remember whether you're doing derivatives or antiderivatives. It's the same either way. And so we get 1 over 20 multiplied by the integral of e to the u du is going to be e to the u plus c. And then we've just got one more step. We need to go back. Our original problem was in terms of t, so we need to go back in terms of t, and we get 1 over 20 times, originally our u was 20t minus 10t squared. Don't forget that constant of integration plus c on the end. All right, our next example, we have the integral of the quantity 7 plus 4 times the natural log of x. All of that is raised to the third power and then divided by x. And so anytime you see a natural log inside an integral, you're going to have to use some kind of substitution because we don't know what the integral of the natural log function is. And so in order to integrate this, we are going to substitute in for that part raised to the power. General rule of thumb is that you will, just like with the chain rule, anything that's raised to a power, anything that's inside another function, be it inside a natural log, inside a exponential, inside a square root, anything like that, that is going to give you a big hint as to what you are substituting for. So we are going to substitute for what is raised to that power there. 7 plus 4 times the natural log of x. We need to replace our dx, so let's take the derivative of both sides. Derivative of 7 is 0. The derivative of 4 times the natural log of x is 4 times 1 over x dx. And I do see that I've got an x in the denominator multiplied by our dx. And so here We have part of that differential in, so we can just move the 4 to the other side and leave the rest of it and substitute in for that x in the denominator and our dx. So when we do this substitution, what's highlighted here, raised to the third power is our u, so we get u cubed, and then the x in the denominator times dx is equal to 1 over 4 du. And so we're ready to integrate. We get 1 over 4 times the integral of u cubed. U cubed antiderivative is u to the 4th over 4 plus c. So that gives us 1 over 16 times our u expression, 7 plus 4 times the natural log of x raised to the 4th power plus c. And that's it for that one. One more example here. This one doesn't have exponential and logs in it, but it also doesn't have anything that is really clearly raised to a power or inside another function. Here we have the integral of x cubed minus 4x all over x to the 4th minus 8x squared plus 3. Now, when you don't have anything that should be just obvious that that's what you need to substitute for, then when in doubt, substitute for the denominator. So we're going to let u be x to the 4th minus 8x squared plus 3. So our du is 4x cubed minus 8 times 2 is 16, x to the 1st, and the derivative of 3 is 0. Multiply that by our dx. I don't see anything exactly like that, so I'm going to go ahead and move that to the other side. So we'll get 1 over 4x cubed minus 16x times du equals dx. So we're ready to substitute in. Our numerator, we haven't done anything with it just yet, and so we'll leave it alone. Our denominator is what we called u. Our dx is equal to 1 over 4x cubed minus 16x du. And then I do see that I've got a greatest common factor in that denominator, so I'm going to go ahead and factor that out. And so the GCF of 4x cubed minus 16x is 4 times x cubed minus 4x. And that is what we have in the numerator there, so we can divide top and bottom by that. And we're left with the integral of 1 over 4 times 1 over u du. For some reason my du became a dx. And the integral of 1 over u du, remember that's not a power rule. We can't use a power rule because then we would have our exponent would be a -1. And if we added 1 to that, that would mean us dividing by 0. We can't do that. But remember 1 over u is the derivative of the natural log. So going backwards, we want our integral. So we get the integral of 1 over x dx, whatever those variables are, as long as they're the same, we get the natural log of the absolute value of x. And so this is going to be 1/4 times the natural log of our absolute value of u. Now we do need to include those absolute value bars there because in the form 1 over u, as long as u is not equal to 0, that is defined, but our natural log function is only defined for positive numbers. And then we've just got one step to go back in terms of our original variable. And so instead of u inside those absolute values, we have x to the 4th minus 8x squared plus 3. And that is our antiderivative. All right, I'll see you guys next time.